So in the previous section 5.2, we have learned that if you want to successfully breed sheep, you should care about the spectral radius of your birth rate, death rate matrix A. What else can be said about the spectral radius? In lemma 1.2, we have learned that the spectrum is always a bounded set, and in the proof we have quantified this to the following: the modulus of every spectral value, and hence the spectral radius, is less than or equal to the norm of A. In fact, now that we're talking about the spectral radius in a little more detail, let me come back to the definition and make one more comment, because now we have time for that. So here we say that the spectral radius is the supremum of modulus lambda for all lambdas in the spectrum of A. In fact, in lemma 1 we showed that the spectrum of A is bounded, so that this will give you a finite value, and is closed, so that the supremum will even be attained. So in fact we can replace sup here by max, which means yes, there is a point in the spectrum for which this circle around 0 that just about covers the spectrum touches the spectrum. Okay, so we have this bound, the spectral radius is less than or equal to the norm of A, and the question is, how generous is this bound? So we know that, yes, the green circle around 0 with radius norm A covers the spectrum, but the red circle, which has just the right radius, which is the spectral radius, also covers the spectrum and is a lot smaller. So the question, how generous is this bound, means how different is red from green. So for example, when we think of a matrix A like this, we see that its spectrum is just 1. So the spectral radius is just the number 1. But of course the norm of A is a lot larger because there is this 5 entry in here. So yes, red and green can be as far apart as you want. You could put 500 here. Now let's try the following trick. If lambda is in the spectrum of A, then lambda square is in the spectrum of A square. You know this for eigenvalues, and it still holds for spectral values. So this here implies that the modulus of lambda square is less than or equal to the norm of A squared, because this is a spectral value of that. Now here you can simplify, and here you use submultiplicativity, and you arrive at this new inequality for modulus lambda and norm A. So if we just take the square root, then we get the good old inequality that modulus lambda is less than or equal to norm of A. Okay, well, here we have been generous, okay? The norm of A squared is less than or equal to norm of A times norm of A. That's usually not equality. But after taking the root, we arrive at the same inequality that we had before, which means these outer terms are just as good as the ones we had before without the power 2. But if we're generous here, then this inequality from here to here must have been better than this. Okay, let's try and better understand this by going to higher powers. So take any natural number n, and note that if lambda is in the spectrum of A, then lambda to the power of n is in the spectrum of A to the power of n. So just like in the case n equals 2, we conclude that the modulus of lambda to the power of n is less than or equal to the norm of A to the power of n. And now we transform both sides, this one here by equality, and this one here by an inequality, by submultiplicativity. And this inequality here is getting more generous the larger the power n is, because you're applying the submultiplicativity rule more and more often, n times, or n minus 1 times actually. Okay, and now just like in case n equals 2, you're applying the nth root, so that here you get modulus lambda, here you get norm of a, and here of course you're still less than or equal to. So in the end you didn't win anything, you still have the same old inequality that we did have without looking at powers n. But now let's also take into consideration what happens to that term here. And this turns into the nth root of norm a to the power n. And you still have this inequality here. But if these two here don't move as you change your n, and this inequality here is getting more and more generous as you make your n larger, then this must mean that this term must get better and better in the sense of closer and closer to modulus lambda as n goes to infinity. And this is the key observation already. So we have to take a closer look at this green sequence of real numbers. Okay, so call this sequence little rn, and in the same style like we argued up here, you can see that your sequence Rn is monotonically falling, right? So we said this green property has to come closer and closer to the left as n grows. So it's monotonically falling, and of course it's bounded from below by 0, because norms and of course nth roots cannot get negative. So it must be convergent. And it turns out that the limit is exactly the spectral radius, so it's the red radius here that we were looking for. And this is Gelfand's celebrated spectral radius formula. Why is it celebrated? Well, it's kind of aesthetical. It's somehow unexpected. Why is it unexpected? Well, because the right-hand side, the spectral radius, is an algebraic concept. I mean, spectrum is defined in terms of invertibility, non-invertibility. So that's all about finding an inverse, yes or no, which is algebra. And the left-hand side is about norms. So the norm of an operator is the supremum of something. So this is analysis. And then roots and limits is again analysis. So here analysis meets algebra, and that's of course interesting. And the other thing that it shows is that it's completely independent of the concrete operator norm that you're using, as long as it's subject to these rules here. Okay. Well, we should at least give a sketch of a proof. Okay, we argued about the existence of the limit before, and we argued about the monotonicity of that sequence before, and we kind of agreed that yes, it's coming closer and closer to the spectral values, but how do you know it ever reaches the spectrum? Okay, and that's where we come back to the function f that we had before in lemma 1.3 proof, where you look at the inverse of a minus lambda I as a function of lambda, which by the way you sometimes call the resolvent function, so we should better call it little r, but in this section we are reserving r for the spectral radius. And then we already saw in the proof of lemma 1 that this is equal to minus 1 over lambda times this series which comes from the Neumann series. And for the convergence of this series, we assume that lambda is sufficiently large. We did all this before. And then you see that in this function of lambda, lambda appears as 1 over lambda here and as 1 over lambda there and nowhere else. So let's substitute 1 over lambda for another letter. Let's call it mu. And actually, let's even be the minus sign here, part of the substitution. So you get this expression here. Now, of course, you shouldn't call it f of lambda anymore, because lambda doesn't appear in here, only implicitly via the substitution. So we can, of course, rewrite lambda as minus 1 over mu. And then call this function maybe g of mu, where g of mu is just f of lambda, but lambda is minus 1 over mu. Okay, now we have rewritten everything in terms of mu instead of lambda. And if we're looking at this, then we see a function of a complex variable mu, and it's obviously a power series in mu, but the values are operators. So it's an operator valued power series, and it becomes operator valued because it has operator valued coefficients. But for a power series, even for an operator valued one, you have this formula for the convergence radius by Cauchy-Hadamard. You sometimes call it the Cauchy-Hadamard radius formula. And even if you didn't call it the Cauchy-Hadamard formula, and of course you didn't do it for operator valued power series, you will remember it from your analysis 1 or probably 2, but I guess 1 course. So the convergence radius is 1 over the lim sub of the nth root, and now you take the modulus of your nth coefficient. And the only thing that changes when you take operator valued coefficients is that instead of taking the modulus, you take the operator norm. And here goes the nth coefficient of your power series. And of course, you already recognize the quantity that we see down here. It's just the one that we claim to be the spectral radius. And by the little analysis that we did before, we know that the lim sub is actually a limit. So let's just drop the sub. Okay, but we still have to argue that it's equal to the spectral radius. So we're not much further, but actually we are. We just have to try and understand what convergence radius of G means, and then we are there. Well, here our function G is this power series of the complex variable mu in the complex plane. And its convergence radius is capital R. And then if you learned about power series in the complex plane, then you learned that the convergence circle or disk ends here because it hits an obstacle, a singularity. So there is a point, possibly one of many, where G is singularities. G is not defined there. Okay, and now let's perform our change of variables. So let's turn mu into lambda by this transform. So lambda is minus 1 over mu. And now you just take this picture over here and perform this transform to every single point over here, which turns the function g into the function f. So in particular, the blue circle will still be a circle under this transform, but its radius now is 1 over the radius r. And while G was convergent in here, now F is convergent out there. And this red set of singularities now gets reflected inside this circle here. And if that red set over here was unbounded, then this is even including 0, and if not, then not. But the interesting fact is that because this one was touching the green circle or the green disk, now also that red set is touching the green annulus or the blue circle that is surrounded by the green part of the plane. And now this red area over here is marking where f is singular. But if you're looking back to the definition of your function f, then you can see that the points where it's singular are exactly the spectrum. It's where the inverse of a minus lambda I is not defined. So this red set is nothing but the spectrum of A. And this blue radius 1 over r must now be equal to 1 over this expression, which means it's just the limit down under. And that's how you see that indeed this radius is so small now that the corresponding circle surrounding the spectrum centered at 0 is touching the spectrum. Okay, and that's how you see that it's indeed the spectral radius. Proof is over.